All right, I told you, and I decided we've got to do some of these proofs, that page, that 20 that I stumbled around here, I'm going to give it a try. That proof for B on 20 on page 112. And it was 20B. And it says, you know, what we have is we have A, B, and X are n by n matrix. And A, B, and X minus, no, A minus A minus AX are invertible. And they want to prove that it says solve for X. What they want to do, they want to solve for X when A minus AX invert equals X invert B. Okay. Now, in this process, what we want to do is we want to do, I better give up now, I can't even copy this. A minus AX invert. What we want to do is we want to invert both sides. Now, if you look at film 8 and you look at B and A, you can say that they, I think I got too many brackets. You can say that this thing right here is A minus AX. Because theorem 8 that's actually in the next section. That's a compilation of everything. That B and A is a row equivalent. Let's have this. This invert is the invert in reverse order. Right? This thing, if you do the invert of the invert, this one, then you get this. And this invert right here is reverse order of the matrices inverts. So then what we have, we can take away the brackets. and then this is B invert. And this, because x is invertible, invert's invertible, then this is just going to be x. Now, if we add the ax to both sides, add this to both sides, we have a equals ax plus b invert x. And then if we take the x out on the right hand side, b plus and then if we do the invert of this thing on both sides, then we do left hand invert. Okay. The argument has to be made that this one right here, this term right here, is invertible. And if you look at theorem 6b, okay, so well, we have to verify that this thing is invertible. And 6b says if A and B are n by n invertible matrices, then so is AB, and the inverse of AB is the product of the inverses of A and B. So by that theorem, this AB inverse is invertible. And before we take the inverse of that, we have to say, show that it's invertible, and that theorem says that if a product of matrices is equal to an invert, then each of the two matrices have to be invertible. That's what actually it's saying. So that says that A plus B invert has to be invertible. And you can get that out of that theorem 6. What's that? I'm going to remind me to go down there and get some. So because A plus B invert is invertible, we're going to take the invert of that times both sides. And that makes this thing I times X, and then this is A plus B invert, the invert. Okay. So X then is equal to this. And we've shown what they wanted to have us show. What's that? Oh, yeah, this is the identity. You're talking about this thing right here?
Yeah.
That's the identity matrix. And if you take the identity times any matrix, it gives you that matrix. You know, identity matrix is that row ones, diagonal of row ones. And so you multiply that times any matrix, it always gives you that matrix back. Okay, let's look at 22. Oh, I got it. It says, explain why the columns of an n by n matrix A span Rn when A is invertible. So if we look at theorem 5. Look at theorem 5. It says if A is an invertible n by n matrix, then for each B in Rn, the equation Ax equals B has a unique solution. So then A has a unique solution. And then Ax equals B, you can do A inverse Ax equals A inverse B, and X then if you look at theorem 4, if A is invertible, then you look at theorem 4 on page 37. And it's saying that A is an n by n matrix, and the following statements are logically equivalent. That is, for a particular A, either they're all statements are true or all false. And then it says that, notice, the columns of A span R, and then it says for each B in R, the equation Ax equal B has a solution. So, because this has a solution, then by theorem 4, this is A of theorem 4, then it says that C of theorem 4 is true, and A spans Rn. That's why I'm saying, we've got to have all these stinking theorems on the sheet, so we go back and look at it. Otherwise, you can't do these problems. Okay. I'm gonna look at the next section. And here in this next section, they're actually bringing a bunch of things together in Theorem 8 that we have that we have looked at. It says, let A be a square n by n, then the following statements are equivalent. That is, for a given A, the statements are either all true or all false. So they're telling you there that if one of them is false, then the other ones are false. So you can use it both ways. You can say this is false, and then therefore, if A is false, then therefore L is false. And if A is true, then therefore L is true. So it says A is invertible matrix. If that's true, then all the rest are true. Or if the next one is true, then that one is. It says A is row equivalent to an n by n identity matrix. A has n pivot positions. The equation AX equals 0 has only the trivial solution. The columns of A form a linearly independent set. The linear transformations, X equals A. X is 1 to 1. The equation AX equals B has at least one solution for each B and R. Columns of A span R. The linear transformations, X, that transformation to R, Rn to Rn. There is an n by n matrix C such that CA equals I, and D such that AD equals I. And the transpose is invertible. So it's bringing a bunch of the things that we have previously assumed or proven, I guess, in the book together there. But nevertheless, I'm going to try to compile all those theorems so we can see them all in the group. Now, draw your attention to that last paragraph above that box at the bottom. It says, because Theorem 5 in Section 2.2, Statement G in Theorem 8 could also be written as the equation AX equal B has unique solution for each B and R. And then it says this statement implies B and hence implies A is invertible. So, and we've got to have access to those other theorems. Then it's at the bottom it says A and B are square matrix, then A times B. If A times B is I, A and B are both invertible. B equals minus A invert, A equals B invert. And 115, top of 115, in that paragraph toward the end, there's a statement that says, which I tried to allude to, that says the negation of a statement in the theorem, this theorem 8, describes a property of every n by n singular matrix. For instance, an n by n singular matrix is not row equivalent to In, does not have a pivot position, and has linear dependent columns. So they're saying all the negations of those things then are true. If one of those negations is true, then the negation of all the others is true. And they're going to give it, there's this theorem 9, linear transformation A be the standard matrix for T. T is invertible if and only if A is invertible. In that case, the linear transformation S given S of X, A inverse X, is a unique function satisfying equations 1 and 2. Now that numerical note, they're saying, but in practice you occasionally encounter nearly singular, or ill-conditioned matrix. They're making a statement there. And they say round-off errors sometimes can make singular matrix appear to be invertible. But you have to be careful with that kind of a situation. All right, so what we're going to do is we're going to look at some problems here. Okay. Page 117. And we'll move to it, saying that unless otherwise specified, assume that all matrices in this exercise are n by n. Determine which of the matrices in exercise 1 through 10 are invertible. 2. Minus 4. 6. So, it might not be apparent, but one of these columns is a multiple of the other. And you can see it if you do the determinant of A. And the determinant is AD minus BC. And remember that this is, it's A, B, C, and D. So then the values are minus 4 times a minus 9 minus, that's 6 and 6. So this is a plus 36 and this is a 36 and that equals 0. So these are not invertible, because if you look at theorem 4, it's 105. It says that if that determinant then not invertible. So let's look at 4. And it is minus 7, 3, and 2. Okay, because this column is zeros, then this is not linearly independent. And then theorem 8, E matrix, because if it's not independent, then E is true means A is true. Implies theorem 8A. Now, if you think about it, if you tried to get this thing in reduced echelon or echelon mode, you could never get a 1 in that column because there's zeros. So, if you were trying to get it as a 1, 1, 1, 0, 0, because this column right here has all zeros in it, you could never get this thing, right? Column of zeros will not allow you to get an inverse. You need to be able to. Because it's a transposition of the identity element into the matrix, or the matrix into the identity, and it'll never happen. Okay. What we could do with this thing is we could try to get this in echelon form, and so what 1 minus 5 minus 4 0 1. So we would add 3, so we go 0. We take 3 times the first row. That's 15 minus 9, and that's minus 12. Then we could go. Then if we took 3 times the second row and added it, we would get that kind of thing. And if you look at theorem 8c, A has n pivot positions. It's not met. Because there's a pivot position there, but this is not a pivot. So because theorem 8c is not met, then implies that theorem 8a is not met. And matrix is not invertible. No, I guess it's maybe obvious. what we have is we have a pivot position everywhere. And if you look at theorem 8, and you look at C, it says A has n pivot positions. Then that implies theorem 8, A is true. The matrix is inverted. So it's just using that theorem 8 to work out why something is true. Okay, number 12. The first statement A says, if there is an n by n matrix D such that AD is I, then there is also an n by n matrix C such that CA is I. Okay, if AD equals I, then theorem 8 K is met. Right? And this implies that CA equals I, theorem 8J, and therefore that statement is true. So what do you think of B? You're going to have to use 8. It says if the columns of A are linearly independent, then columns of A span. So columns A linearly, what's it say, linearly independent. So what, if you look at the theorem 8, so what is being said that they're true? What part of theorem 8? Okay, so this then theorem 8E is met, right? And if 8E is met, the thing that it says, then the columns of A span R. So do the columns of A span R if E is met? By what statement? Okay. So you're saying H, right? So we'd say columns of A are linearly independent. Theorem 8E was met. And then A spans Rn by theorem 8H, right? You understand? You're saying one is true, therefore you look in the theorem, and if the theorem says that is true, then the theorem is saying that if it's true, then all the other things are true. So therefore, then you can look and see if what you're asked to prove is one of those other items. And then you can say, therefore, this is true because theorem 8H implies it. And then you'd say, therefore, the statement is true. Okay, 22 plus 12. 12C. Okay, 12C says if the equation AX equal B has at least one solution for each B and R, then the solution is unique for B. So what do you think we're going to do? So the statement statement AX equals B has at least one solution for each B and R. So which in theorem 8, which one of those is that? Okay. Let's see. Is met, right? Therefore, all those other statements are true. So how are we going to use the rest of the statement to say what? What's that? Really?
Well, if you're going to pause class, go play in snow, I guess. Snow's the best.
Okay, what we have to do then, we have to show that the solution is unique for each B. Okay, there's a theorem 5, section 2.2. Says that A is invertible n-by-n matrix. Then for each B and R, the equation AX equal B has a unique solution. So that statement, this statement right here, implies that this is met, right? And then theorem 8A is met, which says that A is invertible, right? Which states A is invertible. And then if A is invertible, then by theorem 5 on page 106, A has a unique solution. AX equal B has the unique solution, which is X equals A inverse B. And therefore, the statement is true, right? It's true. That makes sense. So D, 12D, says if the linear transformation maps Rn into Rn, then A has n pivot positions. Now notice, in order for n pivot positions, so in order for n pivot positions to exist, how do I say? See that theorem 8C would be met. which implies that in 8I should occur, and that says linear transformation x into ax maps R n onto Rn. Therefore, the statement x having ax maps Rn into Rn is incorrect. And statement is false. Okay. Proofs are fun, aren't they? What? You like proofs? Huh?
How often? Sometimes. They're easy.
And these are, I think, easy, but I don't think they're easy, but they're easy compared to a lot of proofs. Okay, this E is stating that there is a B in R such that the equation AX equal B is inconsistent. So if there is a B in R such that the equation AX equal B is inconsistent, then the transformation is not one-to-one. So that statement B in R. Yes. R can such that the equation AX equals B is inconsistent. If you look at theorem 8G, it says the equation AX equal B has at least one solution for each B and R. That's a negation of that one, right? B is in R such that the equation AX and B is inconsistent. If it's consistent, it has one, right? If it's inconsistent, it has none. So that statement says that this is a negation of theorem 8. Which one is it? G. And then the theorem EF is negated. And F is saying the linear transformation is 1-to-1, so the linear transformation is not 1-to-1.
The condition, which of the is G as a loose constant. Well,
What's that?
with this, since our condition is that, I'm sorry, I'm trying to think through the conditional logic. When this statement is technically true, since our condition is false.
See, if it says it's inconsistent, and then theorem G says the equation has at least one solution. If it's inconsistent, it does not have one solution. It has many solutions. And this statement says that B is in R such that equation AX and B is inconsistent. So that statement is a negation, says negation of 8 is true.
The answer is technically, it's vacuously true since we negated our condition.
Oh, well, the ultimate statement is true.
Yeah.
Yeah,
Okay.
yeah. You're jumping on me. Okay, that statement says that the negation of this statement is true. And then theorem 8, F. And 8F says the linear transformation is 1-to-1. Then that statement has to be negated. Right. Okay. Then is negated. EF. And that statement says the linear transformation transformation is 1-to-1. So the negation of that statement is true because G is negated, then F has to be negated, and therefore, as Ryan said, what? Right, Raylan, that the statement is true because it says if B and R such that the equation ax of b is inconsistent, which is a negation of g, then the transformation a to ax is not one-to-one. So the theorem says if g is true, then f is true, which is one-to-one. So if the negation of g is true, then the negation of f is true. And therefore the statement is true. Okay. Enough of that fun stuff. So then let's look at 14. It says M by N is a lower triangular matrix is one whose entries above the main diagonal are zeros. So it's just saying that you have this main diagonal, which is A, B, C, D, whatever it is, and you have values down in here, which are A1, A2, A3, D1, D2, and then C1, and then everything up here. Everything up here is this. This is 0, 0, 0, 0, 0, 0. This diagonal and everything below has numbers in it. I don't have it written, but I get it. That's a lower triangular matrix. It says when is a square lower triangular matrix invertible? Justify your answer. Well, by row operations, row operations, you can interchange your rows. So what we'd have is we'd have this A. We could actually take A3, B2, C1, and D. That would be this last row, and put it in the first. And then we could do let's see, do that. We can interchange it. So then we'd have, down here at the bottom, we'd have I had this thought out. Let's do it this way. If we start out with this row, we can multiply by this row to get this A1 to be 0, right? So we can put 0, and then we can put zeros here and there, right? And then what we'll have is we'll have this B, which is going to be unchanged, right? We'll have 0, 0, and we'll have B1 and B2, and then we'll have this C that's unchanged, the C1, and then we'll have D. we'll still have this thing, but we can change that first one out, and then we can go and do, we can do an A, 0, 0, 0. We'll have a Z, B, 0, 0, and we can use this B right here to make these two positions down here 0. And we'll not change those other ones. So then we can have a 0, 0, and because when we use that B to change that, it won't change that column. And we can get this rest of this column in zeros. And then we'll have a C, C1, and a D. And likewise, we can use this C right here to change that one below it. So then we'd have an A, 0, 0, 0, 0, B, 0, 0, 0, 0, C, 0, and 0, 0, 0, D. And I think we've shown that what we have is we have n turning points. We 8C, A has n turning positions, and therefore A is, theorem 8A says it's invertible. Okay. So is it time? Yes, time. Okay. So Tuesday,